Good afternoon, everyone. Welcome to the Monsoon Cafe. So, today I'm gonna talk about the how Upper Ocean responds to a passage of a cyclonic storm or hurricane, whatever, at very fine resolution, which is less than 10 kilometers. So, from traditional point of view, when there is a passage of a cyclone, if you see observational data or coastal model data, so when there is a cyclone passes or hurricane passes over the ocean surface, mostly it's the like game on the density stratification, which is mostly the vertical component of the stratification, and due to momentum flux or heat or freshwater or salt flux, and these components compete with each other to dominate the whole stratification process. But in recent studies, there has been some findings with finer resolution with the advancement of model technology. So it's like 1 kilometer or even more less than that finer horizontal resolution model. So vertical processes are important, but lateral or horizontal processes are also important, especially at sub-mesoscale, which is 10 meter to 10 meter to 10 kilometer. So, and these are like consist of very small vortices and fronts, like sharp gradient of any quantity, especially salinity and temperature, and filaments, like very small, like a few kilometers of line, like intrudes inside like ambient uniform water in temperature and salinity or even in density. So today I'm going to talk about basically the major key findings from this paper. This is a German group from Leibniz Institute, and they have taken Baltic Sea as their natural laboratory. And their study period is October to November, and this is the model domain. These cyan color lines are the open boundaries, and within that domain, they have taken this red box, which is their study region for this filaments and frontal regime. And they have 100 vertical levels, mostly concentrated in top 50 meters, because submesoscale regimes are very active in very few meters from the surface. And also I'm going to talk about my own results of my research, which is related to this kind of work at the end of this presentation. Okay, so model configuration. So they have used GTEM General Estuarine Transport Model. And this is like ROMs only, 3D hydrostatic primitive equation solving model. And models are solved in Arakawa C grid with a finite volume and grid a spherical grid. And they also use a Bosnian approximation for nearly constant density inside the mixed layer depth. And yeah, so and here they have used little like it's like a terrain following like their vertical layers are not depth, it's terrain following like sigma coordinates only, but it's little bit modified because these coordinate vertical layers follows the vertical diffusion equation, because they are resolving very small or fine resolution structures. That's why they have stressed on vertical diffusion. Yeah. So horizontal resolution. Yeah. Horizontal resolution is 500 to 600 meter. Actually, the for whole domain is 600 meter. This is a nested domain, which is 500 meter. And reason for this, because Rossby first mode of Rossby baroclinic deformation radius is nearly 1 kilometer at that latitude. So that's why they have taken little lesser resolution, finer resolution. And this is the kind of their validation for their like model output. So this is they have taken BSH, some German product, SST product, and this is their model output. You can and As this is their this is the island, Gotland Island, and this is the coast of Latvia. So within that region, they are focusing on their study. So at that region, SST simulated very well from their model, but towards northern side, model estimated more SST, and near the coast of this island, there you can see very nearly 8 to 9 degree of SST, which is followed by a storm event, which is their interest because storm event induce some cold water upwelling from the subsurface and pushes the warm water towards the Latvia coast, which actually creates the very sharp lateral gradient of SST. That's how this sub-mesoscale regime appears. And if you see at this point, they have some like in situ data from CTD. So they also compared the output. This is on a particular day. This is the day when first storm surge starts. So 18th October 2017. For a particular day at that point, at the center of that their like nested domain, they already checked the temperature and salinity profile, which is nearly very good. Little discrepancies are there, but they are very less. So that means model has simulated even vertical also. They have a very high, very excellent simulation is there. So this figure is very important. Here they have identified nearly 3 pulses of storm events. First, nearly on 18th of October, which has like south and southeasterly winds. Then second, after that, there is a calm weather for nearly a week. Afterwards, on 25th of October, they have the second charges of storm. Again, there is little nearly a 5 days of relaxation period. Then again, there is a storm, which is in opposite, like it's towards southerly direction. Sorry, yeah, northerly winds are there towards southern side, which is for 2 days, 30 and 31st. And they also check the buoyancy component, which is the buoyancy flux, which is contributed from both heat flux and freshwater flux. And also this red line is the air temperature. So, and here positive value of buoyancy means the loss of buoyancy to the atmosphere. That means more unstable condition, more mixing and all. So you can see once this storm event starts, there's a lag, little bit lag is there, but once the storm starts, buoyancy also start increasing. That means more instability is there and air temperature start decreasing. And this is for every event you can see. So this is just after the storm event on the 19th of October, first storm event. So they have plotted these frontal structures are defined by few parameters like as like SST. Then this is the relative vorticity normalized by Coriolis force, which is nothing but the Rossby number. This is horizontal divergence divided by Coriolis force. And this is something called frontal sharpness, which is the buoyancy, lateral gradient of buoyancy. And this is the vertical velocity at 2 meter depth. And this is the balanced Rossby number. And they have marked a region, very small region. You can see very sharp. You can see very beautifully there is because it's following this temperature like front. This Rossby numbers are following the same pattern. Even frontal sharpness, even Rossby this balanced Rossby number, researcher number. And this is the nearly monthly average from October 15 to November 15, the monthly average of sea surface temperature overlaid with surface current. You can see there is a consistent sharp like lateral gradient of.
That is monthly average. What is this?
This is a daily snapshot.
This one, this SST and that SST.
This is a monthly average.
Huh?
And this is a daily instantaneous snapshot on 1453 19. Yeah, 1 day just late, 1 day after the storm. So they also check the whether this event is this area is abundant with submesosphere regime or not. That's why they just check the monthly average of SST. Here you can see not as sharp as like this plots, but here because this is a monthly average, but still you can see there is a gradient of a coalescence like nearly 7 or 8 degree SST, and just after few kilometers 12 to 13 degree of SST. So they zoomed in the next figure. I'll show the zoom version of these three parameters. So here you can see this is the frontal sharpness, nothing but the buoyancy vertical, like horizontal gradient of buoyancy. See, you can see, and they have set some criteria like 10 to the power minus 13, 1 into 10 to the power minus 13 unit of this sharpness should be there. Then only they will plot it. They will like plot it. Otherwise, they will discard the other like values. So that's how, in a control format, you can see very beautiful and very narrow, nearly 6 kilometer, 5 kilometer like frontal structure, and which is also mimicked by the Rossby number and researcher number. So here this Rossby number along this very sharp along this parameter you can see a positive Rossby number, which means cyclonic vortex along that line. That means upwelling, or upwelling means cold cyclonic this filament. They also check the mixed layer depth modulation during the period of the cyclone. So this is like just after one day after the this first event. This is 2 days after 2 or 3 days after the third event. So here you can see like this pattern. You can see shallow mixed layer mimics the same front. And here also frontal sharp. This is also frontal sharpness, also mimics the same pattern. Because just after the first event, because first cyclonic event was not that strong, but it was a cyclonic event not that strong, and just afterwards there is a calm weather. Also there is a constant upwelling from the subsurface, which is constantly creating a horizontal SST gradient. So there is a kind of a mixed layer restratification, though there is a cyclonic event, but and normally cyclonic events or wind try to mix the upper layer, so try and kill the certification, but due to these small filaments and all, they try to restratify along their filament and front. So that's how there is a secondary azeotropic circulation which try to actually restratify the uniform mixed layer. Yeah, so to check this more clearly, they have divided their region with like a frontal region and non-frontal region. So they have taken this criteria. So if frontal sharpness or lateral gradient of buoyancy is lesser than this like quantity, then it will consider in non-frontal. If it is more than that, that is considered as frontal regime. So based on that, they have checked the coverage within that red box. So during the first period of their studies, during the first, and these, I don't know, you can see there is a very little dark patch of gray vertical column. So there, those are the three like these events, storm events. So once storm event starts, this frontal region start decreases because of the mixing, but still it dominates. And this red curve shows the non-frontal region within that box. But afterwards, winds get stronger, and that's why frontal region getting minimized, and non-frontal region dominates. And here also they have divided mixer in three regions. So what they have done, they have area averaged the entire domain for mixed layer depth for this period, and also check the using this criteria. They have selected the frontal region. Over that they have area average the mixed layer depth, or for non-front also they have averaged the mixed layer depth. So you can see, and also these dotted lines are wind speed. So you can see total mixed layer depth is mostly contributed from the non-frontal like mixed layer depth. And which is little deeper, like more nearly 25 to 30 up to 40. But non-front for frontal region, that is the blue curve. This mixed layer depth is always shallower. So that means that means the though there is submesosphere regime here and there, but and most of the region is still dominated by the overall general circulation of the basin. So here I'm going to show about little about my own research. I'm also like this is the result from my previous recently completed simulation, which is little coarser resolution. Like for study of submesosphere regime is nearly 2.3 kilometer in horizontal grid and 40 sigma levels. So I also checked the upper ocean response of cyclone filing, and this is the part of the cyclone and different stages of the cyclone. You can see, and it is a very, it's a very extremely severe cyclonic storm. And here, when I check the SSS difference, like sea surface salinity difference, I found this region very interesting. Here you can see very sharp gradient of because it's a difference. It's a difference between P storm and post storm. P storm is like 1 to 7 October, and during storm is like 11 to 13 October. So I just take the difference. So here I can see, and this is actually high salinity water is along the EICC, and there is a ED pre-existing ED sitting there, which actually try to emanate the water east southward. So I check this box, and I try to plot the same parameters they used. So this is just before the arrival of the storm, uh, and frontal frequency I plotted. So this is SST, this is SSS, this is horizontal divergence, this is Rossby number, this is vertical velocity, and this is frontal sharpness. So here in temperature also there is some filament kind of structure is there, but which is more prominent in salinity. Which is actually not surprising because in Bay of Bengal, density is mostly controlled by the salinity. And I can see, and this is a cyclonic ED, that's why Rossby number is positive. But in between that, there is an intermediate negative, or maybe not negative, very low value of Rossby number. That means some kind of anticyclonic azeostrophic circulation is there. And here also, because it's a cyclonic ED, so there is velocity is almost upward, but there is intermediate value of downwelling. And here also it's very clear. And this is called frontal sharpness, horizontal gradient of buoyancy. So which is following these filaments. And this is the snapshot of 12-hour UTC, 11th October, when cyclone is somewhere here, is before entering here. This is just one day after the storm. You can see this frontal structure is nearly vanishes here. That's why you can see nearly this cyclonic, it is nearly upwelling favorable only, cyclonic. And here also frontal sharpness is slowly decaying. So yeah, but still I have to do a lot more work because its model is little coarser because their resolution is 500 meter. My resolution is little more than 2 kilometer. So wait, like that's my the future plan to run at least 1 kilometer model to start from this point. Yeah. So, so in conclusion, so they focused on the Baltic Sea, which is like a very rich ground of potential frontal structures. They check this general circulation and wind pattern actually reinforce their uh, like upwelling, which actually gives the sharp lateral gradient of SST, which actually the first trigger for this submesosphere regime. They also plotted the various quantity like frontal sharpness, Rossby number, researcher number, which is favorable for this regime. And they also found that this in between two storm events, these filaments try to reappear and try to restratify the mixed layer depth. And they also check the later aerial coverage, but non-frontal regime is prominent over frontal region, but still whatever it is, it try to restratify in a very efficient way. I also check my own research, so it's I think I can proceed over because I can see some submunicipal regime. Yeah, thank you. Yeah.
When you said upwelling happens, this filament, is it on the filament or next to the filament? That filament is blue.
See, this is a filament.
Can you go to the SST graph?
Yeah.
Previous. Where they show SST of the right. So on the right side, B top.
This one, right?
Yeah, no, right side B, that is the figure B.
This one.
Yes, and there that thing is, the filament is red, right?
Yeah, so this red color means this positive means cyclonic vorticity because it's a Rossby number, positive Rossby number. Negative means kind of a negative vorticity. So you can consider along this red line or elongated red curve, whatever you say. So there is a upwelling. It's a textbook knowledge that when there is a cyclonic vorticity, we can consider some portion of upwelling is there. But it is surrounded by a very negative Rossby number, which is actually anticyclonic in nature or downwelling. So this and here you can see Rossby number is very high, both in even in the intermediate inside the filament, high negative Rossby number and surrounded by positive high positive Rossby number. So when there is geostrophic circulation for larger circulation, geostrophic circulation, Rossby number is very less. Here Rossby number is very high. That means there is a portion of azeotropic circulation because it's so small. Planetary rotation affects not totally. Like it's maybe partially it affects, which is the interference from this figure.
So this structure is one single structure.
No, it's a you can see continuous structures.
No, that box you have, cyclonic and anticyclonic thing. That is the result of a storm. The storm was over that at some point.
Actually, due to the storm, no, there is a strong upwelling of cold water here, and it pushes the warm surface water here. So, which creates this front just after the after a cyclone, like storm, just create the front. Due to this, sharp gradient of SST, these parameters appears. Yeah, storm is like a trigger for this sub mesoscale regime.
Thank you.